Hello, my name is Chris Kerslake. Welcome to my Thesis Defence, The Code is Lava, Improving Children's Debugging Skills with Explicit Instruction. Now this was part of my master's thesis defense that originally occurred on August 25th, 2023. And this is a re-recording after the fact because unfortunately that recording or that event wasn't recorded. So this study takes place in fall 2022. It was an 8-week Python programming course where students learn Python programming with turtle graphics. And I looked at how novices debug their code during this course. Now the title, The Code is Lava, comes from the pilot for this program, where a student, upon seeing one of their debugging challenges, said, "It's like the code is lava. I've got to pay close attention. Look what I'm doing. Plan ahead." I thought, what a great title. So I'll start with some background about how I got here today and how I came to look at debugging. So in the 1980s, early 1980s, my elementary school purchased its first computer. No one knew how to use it. It came with a book. I picked up the book and I used the book to help me get started learning how to be a computer programmer. I continued through high school and into university and completed my undergraduate degree in computer science in the mid-1990s. I then transitioned to being a professional computer programmer for a number of years. And then in 2005, my son was born. And a few years later, when he entered elementary school, I approached the elementary school and said, "What kind of programming do you do?" "Computer programming." And they said, "Well, we don't do computer programming in elementary. They do that in high school." So a little bit perplexed, I asked if they would mind if I tried to teach a computer programming class. And after a bit of wrangling, they said yes. And I did what any good computer programmer would do. I went and Googled how to teach computer programming and used that to help me build up some lesson plans. Now, I've been teaching that for about 8 years, having a great time. But what I've noticed is that when kids encounter bugs, they often get stuck and don't know what to do. And I wasn't really sure what this was and how to do it. And not having many people around me who knew how to do computer programming instruction, some folks suggested that I look into maybe increasing my level of education about how to teach, and that led me to Simon Fraser to look at their education programs, including the Education, Technology, and Learning Design program here, which is what I'm defending my thesis on today. So I've spent the last 4 years in the ETLD program, and I've focused in on computer programming instruction and debugging. So what's the problem I'm actually looking at? Well, imagine that you are a novice programmer and you encounter a bug. What do you do? Well, what I've discovered in my class is that the majority of the students, they just stop, ask for help, and then wait for me or someone else to help them. Now, if they're lucky and they're sitting with a friend, they might look at the code, they might analyze it a little bit or compare the code. And if they're feeling adventurous, they might make a guess and check and see if it works. And if it works, great. And if it doesn't, then they just wait. Now, unfortunately, they don't have a plan. And because they don't have a plan, they don't have any alternatives except asking for help. So why is debugging so important? Well, it's basically a barrier to kids learning how to code. So let's look at the significance. Why is it important? Well, according to Gould and Dronkowski, debugging takes 3 times longer than coding itself. Or as Cohen-Meyer put it, 70 to 80% of the time the programmer spent programming is actually spent debugging. Now, according to Macaulay et al., this is important because if you can't fix the code, then you can't write the code. So again, debugging is a barrier. So that led me to formulate this research study with 2 aims. The first aim is identifying the debugging strategies and challenges that students already have, and then introducing them to some explicit debugging strategy instruction and evaluating the impact of that instruction. So these 2 aims led to 4 questions. What strategies do novice elementary school students employ when debugging Python code? And what challenges do they face when debugging? Then, what effect does explicit debugging instruction have on student debugging strategies? And in what way do students respond to explicit debugging instruction? So, given these questions, I turn to the literature to shape my study. So the graph on the right is the number of debugging-related research papers since the 1970s, sorted by decade. And research into debugging really started in the 1970s. It was empirical studies focused on the output. So this is what kind of bugs, what frequency of bugs. And the goal here was really about improving the performance of computer programmers. So if debugging, as I mentioned before, takes up so much time, then if you can reduce debugging, you can improve or reduce the time that programmers spend programming. And so you reduce cost and time. In the 1980s, though, we sort of shifted the focus towards more of a psychological analysis or psychological study of what programmers were doing when they were debugging. And they were helped by the introduction of a new research protocol called verbal protocol by Erickson and Simon. And the idea here is have the participants explain what they're thinking while they're doing a task or after they've completed a task, and then using those descriptions, analyzing them to try and figure out what were they thinking while they were doing it. Now, this is the approach that I took in my study because I wanted to get to what are they thinking. Now, into the 1990s, the 2000s, and onwards, this has also been a popular approach. And so that's how I shaped my study, was looking at these historical studies, finding the most appropriate approach, and then using that to put together this qualitative study. So let's look at the participants in the methodology. So there were 9 male upper elementary school students, grades 5 to 7, ages 10 to 12. They were tasked to complete 3 debugging challenges during an 8-week course. They used a concurrent verbal think aloud protocol. Concurrent means tell me what you're thinking while you're doing the task, so concurrent with the task. This is in contrast to retrospective, which is tell me what you did. So after you finish, tell me what you did would be retrospective. In addition to the debugging challenges, before and after, or what's called pre and post, I asked them to describe their level of confidence while they were debugging. So how confident are you before? How confident are you after? And all of this was recorded via Zoom. So the study looked like this. This is an 8-week timeline. Each week there was the class was 2 hours. The first hour, again, was the Python and Turtle graphics programming. So those are the little graphics at the bottom. So we started off making simple shapes like triangles and squares. And over the course of the 8 weeks, the students got to more complex models, culminating with the Among Us little video game character in the bottom right corner. Now, during the second hour of each week, that's when the research study was conducted. During the first week, we did our first debugging challenge, and the students were asked to think aloud while they debugged the challenges, and they were asked their level of confidence pre and post. During week 2, that's the first explicit instruction, and I used a novel approach called Stump the Teacher. So the students first of all built an image of their liking using the Turtle graphics and Python, and then they were told, okay, now introduce some bugs to try and stump the teacher. So they went and introduced some bugs into their code. They gave me the buggy code. I didn't know what it did other than they would show me what the working version did, and then I would debug it live in front of them. While I was doing that, I was thinking aloud concurrently to demonstrate both think aloud, but also my expert debugging approach. And then at the end, after I debugged all of the students' projects, I asked them to describe what differences they noticed between how I debugged and how they debugged. During week 3, there was no research. During weeks 4, 5, we did a new challenge. This is the squares in the middle there. So they went from the mixed up squares to the stacked squares. Again, self-efficacy, self-confidence, pre and post the challenge. During the 6th week, I introduced them to the wolf fence algorithm. So for the computer scientists, this is a binary search problem. For the non-computer scientists, this is a divide and conquer. So if your search is in here, you check this half first. If you find nothing, then you know you can focus on this half. And you just keep dividing the problem in half until you locate the source of the bug or the area where you think the bug is. During weeks 7 and 8, they did their final challenge. And again, going from the image on the left to the image on the right, and then giving me a self-efficacy score, self-confidence score. So all of this resulted in a lot of data. So 8 classes, 2 hours per class, 16 hours of video. That was all transcribed, so that was converting it from the video audio into text. I wrote some code to do that because there was way too much. I then focused in just on the debugging problem itself, or the challenges, I should say, and that resulted in 489 pages of data. I annotated them with screenshots and comments so that I could just read through and see what was going on. I then loaded those into some software called In Vivo, which allowed me to encode qualitatively the data. Initially, I started off trying to inductively encode, but I couldn't arrive at a convergence with a second coder. And so I was fortunate to find a code book from a 1984 debugging thesis and from Iris Vesey, and use that along with my inductive codes to arrive at a coherent description. I then was able to arrive at a strong Cohen's kappa, and so I used that code book to encode the rest of the study. Once I had that, I was able to create these debugging episodes down in the bottom right, and those just also come from Vesey's thesis, and I used those to describe the strategies and challenges in the results. So, before I explain what happened or give you results of the data, I want to talk about what previous studies found so I can set the stage for what I should expect to find. So Carver and Clark in 1986, they created a expert debugging process, and they said this is what it looks like when an expert debugs. And then they went and taught 9 grade 2 to 4 kids over the course of 24 hours. So you can think of my class as like 8 hours of teaching, so 3 times as long. They used logo and turtle graphics, and they discovered that at the end that none of the kids had really developed any debugging strategies. So even with teaching coding, they still didn't get debugging strategies. So Carver decided she wanted to fix this. So she did another study. This was a 6-month study, so about 5 to 6 times as long as mine. Similar age kids, again, logo and turtle graphics. And this time she introduced them to some explicit strategies. Unfortunately, by the end of this, she discovered that the kids really hadn't integrated the strategies that she taught into their approach. So fast forward 30 years to Butcher et al. In 2016. Now this is with university undergraduate course. It's sort of a week out of a 12-week semester. They introduced what's called the wolf fence algorithm. That's what I taught my students during week 6. And during that 1 week, they did a lecture, a lab, an exercise, and a challenge. And what they discovered was 2 things. 1, students either got all the bugs or got none of the bugs. So they were either lost or they got it all. And even though they had taught them the wolf fence algorithm, none of the students had actually used the wolf fence algorithm. So again, nobody was integrating the strategies that were being taught. And there was this paradox where either they got it or they didn't get it, which implies that they had some prior knowledge that allowed them. But without the prior knowledge, they, just like Carver and Clark, didn't develop strategies. 3 years later, McKelly and Romiecki, they went and approached high school computer programming teachers and asked them, how do you teach debugging? And they said, we don't. Why not? We don't have any material. So they went and developed some debugging material, went back, taught a grade 10 class. They had 28 students, 13 in the experimental group, 15 in the control group, and they introduced them to the strategy that they had put together, and they measured the effects, and they said, hey, we found a medium impact of doing this. Now, I have a bit of a challenge with this study because the students were not randomized into the 2 groups, and the intervention, the teaching, was 10 minutes. So my suspicion is that because they didn't test for it, there may have been prior knowledge, but they didn't test for the prior knowledge, so the ability to generalize their results is a bit suspect. Now, in that same year, Coe et al., during a 5-week summer camp, introduced high school students grade 10 to 12 to explicit debugging strategies, 2 of them. One was how to debug, and one was how to find answers using Google. What they discovered is that only 13% of their students actually integrated these strategies or used them at all. And so even with great material, an instructor, 5 teaching assistants, and lots of hands-on support, students overwhelmingly didn't integrate the strategies and reverted back to what they did before any of the explicit instruction. So what this means is most kids don't develop it on their own, and even with explicit instruction, they don't seem to integrate it, or that's what these studies imply. So what did I find? So the S means strategy, C means challenge. So during the first challenge, debugging challenge, students would copy and paste their code into their editor. The editor would find an error, it would red underline it, and they would click on it and they'd immediately fix it. So they were using the tool, the editor, very effectively to find and fix simple errors. Even so, some students introduced new bugs while they were trying to debug, and that just made the debugging take longer. Some students also got stuck when they were doing the repair, so they might say, I think this is wrong, not sure what to do, not sure, maybe I should do this, maybe I should do this. Ultimately, all the students were successful. During the second challenge, this is during weeks 4 and 5, I noticed that students started off by reading the code very closely and sequentially, so from top to bottom. Now, I think that this was partially because of the first week, which had syntax errors, so I think they were just looking for the easy syntax errors, but there weren't any. The main strategy they used was guessing and checking. So they would try something, see if it worked, and if it worked, great, they would move on. If it didn't work, they'd back up and try another strategy. Now, that worked reasonably well. All the students, again, solved the challenge. However, I noticed a couple of new challenges here, and one of them was this guessing and checking could be counterproductive in that if you did it a bunch of times, it was sort of like whack-a-mole. You were just trying to find a solution. And unfortunately, for the students, it worked. And I say unfortunately because then it became reinforced in them that I should sort of just guess. And if I guess enough times, I'm going to find a solution. The other challenge that I found here was students working around the bugs. So because they were trying to arrive at a drawing, well, they would fix some of the bugs and then be like missing something, like the 4th line, for example. And so they would just add in extra code to make that line draw rather than fixing the actual cause of the problem. So they would sort of work around or hack in a solution. During the third and final challenge, I noticed 3 strategies. The first one is called run first, run often. Now, during week 2, when I did Stump the Teacher, the one thing that a lot of students noticed and said when I asked them what the difference was, is that I ran the code first and I ran it a lot. In fact, I ran it after every change. And I noticed that some students actually integrated that as part of their strategy moving forward. Now, the wolf fence algorithm that Butcher tried in 2016 and which I introduced during week 6, nobody used it. I mean, there was one student who used it one time during the final challenge. He put one print statement in, ran the code, went, oh, that didn't help, and then just moved on. So I would say they didn't really integrate it. The main strategy that I found was using the debug print statements effectively. The students who used them and used them correctly found the problem and fixed the problem. Now, the challenge side, there was excessive changes again, which were unsuccessful, and some of the students used working around of the problem successfully, but I consider that a challenge because they didn't really get to the root thing. So looking at this data right now, it sort of seems that I'm in line with previous studies because the uptake and integration were limited. However, I want to unpack the final challenge in more detail. So I call the final findings the good, the bad, and the indifferent. Now, for context, during the final challenge, students were given some debug print statements in the code already, but they were commented out, or they were disabled effectively. Now, during the second challenge, I had also put debug print statements, but I'd left them in and only one student had used them. But for this final challenge, you really needed to use the debug print statements to find the real problem. So the first group that had the good outcome, they used the debug print statements and used them effectively to get to the root cause and solve the problem correctly. But to do so, they were overwhelmed trying to do it. They made mistakes, they were really struggling, and they needed a little bit of support to actually get through the challenge. But they found the best fix, and they were ultimately successful. But paradoxically, they reported a loss of confidence. So out of a scale from 1 to 7, they reported 3.6 and 4.1, so just a little above halfway. Now the second group I call the indifferent group, and the reason for that is they kind of more or less skipped using the debug print statements. One of the students uncommented and ran it, said, no, it doesn't help, and then moved on. But these students solved the problem quickest, by far. And they did this by working around the problem. So they found a way to kind of get the right output, but they didn't actually fix the core problem. So they ultimately, although they were successful, it wasn't really the right solution. It was successful though. And when asked about their confidence, they said it hadn't changed at all. Now the third group, they surprised me, and I'll talk about this a little bit more in the next slide. But what happened here is they turned on the debug print statements, and then they looked at them and said, well, this doesn't help me with this drawing problem, and so they ignored them. Ultimately, they both gave up on the challenge, but in two different ways. So the first student tried a couple of things, it didn't work, gave up. I reminded him of the debug print statements. He got really excited, turned them all on, tried again, said, well, that didn't help, and then just quit. The second student tried something, and he just kept trying things over and over again. He tried 15 changes in 10 minutes. The average was 7. And when I asked him what he was doing partway through, he says, I'm just messing around. So he was excessively changing with no real strategy. When he tried to use the debug print statements, he just said, well, those don't help, just a bunch of text, and just ignored them. So ultimately, those two were unsuccessful, and they were pretty downtrodden at the end. So on its face, it looks like, again, the limited uptake, no integration. What does this mean, though? Well, I think group 1, I think they just needed more practice, because they actually used the strategies that were in the class, but they struggled. They were a bit overwhelmed by them. And I think if they had had a little bit more practice when they ultimately used them, they found the right problem. And I think with a little bit of practice, they would have increased their confidence and their desire to use them. The second group, I think they were already at a point where their strategies that they had, which were already fairly systematic, were sufficient for this challenge. So they were able to figure out kind of what was going on, and they found a workaround, and it worked, and so they were fine. I think if the challenge was a little bit more difficult and their strategy of working around hadn't worked, then I think they would have tried, just like group 1, they would have fell back to one of the strategies. But I think if they had seen the value of the strategies, they actually could have used them more effectively, and they would have actually finished sooner if they had. So I think they just needed a little bit more practice to sort of see the value of it. Now, as I mentioned before, the third group, they really surprised me, because their level of confidence all the way leading up to the third challenge were like at 100% or above. Like they were so confident. Oh, this is amazing. I'm great at this, right? And then when they got to the actual challenge, they didn't know what to do. They completely ignored the strategies, and they just sort of fell off a cliff, surprisingly. And so my challenge here is I didn't notice or didn't see any of the symptoms that would have led me to identify that they weren't going to be able to do this. So I think what's missing here is some sort of early assessment tool that allows me to say, like, okay, well, hey, this confidence is really high, but they're excessively doing changes. They don't seem to be systematic. Let me just double check their systematic approach. And maybe I could have identified that early and maybe corrected it early so that they didn't come to the final challenge and have really no strategy and then fail. So what this leads me to conclude is explicit instruction requires more practice and early assessment, so I can sort of correct as necessary. So I see this as my 1.0 study. It provided me with material for articles and a lot of ideas for further investigation. As a result, I hope to continue this research informed by this study to better understand these three groups and their challenges. So let me conclude. I hope these findings continue to advance research into debugging so that more students can view debugging as a challenge to overcome rather than lava to be avoided. Now, imagine you are a novice computer programmer with a plan. Thank you.